Chapter 2.1 Part 2 is going to look at quadratics where we're given a graph and we have to come up with the equation. Our objective here is to write a standard form quadratic given a graph or the key points of the graph. What we're eventually going to want to do is end up in standard form quadratics, but when we're working with a graph, what it's nice to have is actually these two forms, the factored form and the vertex form available to use. And you'll see why, because we're going to have to be using key points from the graph, and those key points, like we kind of addressed in the other video, were the vertex or the x-intercepts or both. This slide really works on notation, and you'll see what I mean in the next slide, but if we have a polynomial function and we have some sort of real number and we're going to call that our solution, what we're going to be looking at then is this type of notation to notate that as our solution. And again, a solution of a quadratic is just the x value of an x-intercept. So how we would notate that is, if our x value of our x-intercept was 3, we would want to write that x equals 3 if I asked you for a 0 or a root. The other thing is, a solution is the same thing as a 0 or a root, so x equals 3, for example. And here we are just saying that a solution is where our function is equal to 0, because it's where our function crosses the x-axis, okay, where our function equals 0. I'm going to be saying this a lot. If you know your roots, you know your factors. If you know your roots, you know your factors. Once you know your roots, what we can do is just slap them into this factor, and the factors are composed of just x minus whatever that root is. Okay? And then finally, as we know, zeros, roots, solutions are all the same thing, and they're the x value of the x-intercept. So if I ever ask you for the x-intercept, I want the point where you would just have that x value, comma, and then of course 0 for the y. So let's look at an example of how knowing all of this is helpful. So if I asked you to look at this given graph, what you would notice is, hey, our x-intercepts are going to be at -4, 0, and 3, 0. Okay, so here and here you can visualize that. So if I asked you for roots, solutions, or zeros, what you would want to do is that proper notation of x equals -4 and x equals 3. Sometimes also they would just write x equals -4 semicolon 3, and they even use colons sometimes, or sorry, commas. So if you know your roots, then you also know your x-intercepts, and we kind of, or vice versa, so we're just going to put that in that form, -4, 0, and I already kind of did this up above there. Alright, and then we have factors. So as I said, if you know your roots, you know your factors, we're going to take those factors and we're going to slap them in. So x minus and then -4, but x minus and -4 would just be +4. And another factor would be x minus, and then our other root was 3, so we're going to put in 3. Factored form then, so as we kind of addressed, y equals a times x minus, and then whatever our root is, we had +4 then, because x minus -4, and then x minus 3. The problem is, for this factor form, we do have to solve for this a, and what we'll want to do is we'll want to pick any solution point that we know will make this quadratic equation true, so that any x, y value that we plug in, we're going to solve for a such that it would make that quadratic true. So I'm going to kind of use the space over here, and what we always try to use is this y-intercept. And it doesn't always work, but if you can use the y-intercept, and I'll address when you can't, but we can in this case, we're going to want to use that, and you'll see why. This y-intercept is 0, -12, so we're going to go ahead and plug in this xy into our equation so that we can solve for our a. So -12 is our y, equals a times, and then our x, which is 0 plus 4, times x minus 3, 0 minus 3. And hopefully you can kind of see why it's helpful to use that y-intercept, because now we just can simplify those parentheses or those groupings. Alright, -12 equals a times, when we multiply those and simplify there, we can get -12. Now this is when we're going to start undoing and getting that a by itself. divide by negative 12, a in this case just equals 1. So what we could do is y equals 1 times x plus 4 times x minus 3, but you don't even need that 1. But otherwise now we can go ahead and get it into standard form, which would require us to FOIL this factored form. So since that 1 doesn't do anything, we can just FOIL these out. We would get x squared plus 4x plus negative 3x, so just plus x, and then lasts plus negative 12 or minus 12. Alright, so there that is. So what I want you to see is we went from identifying those x-intercepts to our roots, and then our x-intercepts because they're very much interconnected, and then these are very connected. We went from the roots to our factors, then we could get it into factored form and just solve for our a, and then we could get it into standard form. So let's look at this one real quick. You learned in the last video a lot about graphing quadratics, so I am going to go ahead and graph this. A nice thing to identify would be our x-intercepts, especially since it's in factored form. So I would set this function equal to 0 to figure out, alright, when for what values of x is this equal to 0, and then we would want to set each one of these factors equal to 0. And what we would get here is x equals 2 is one of our solutions, or x values of our x-intercepts, and then x equals 5. So 2, 0 would be actually the x-intercepts, 5, 0. The next thing that you would want to do is find the vertex. So these were our x-ints. Right? If you wanted our vertex, you could pick the point right in between these x values because we know that that vertex is reflexive, or it has a line of symmetry going through it. So right in the middle of these would be where our vertex was. So you can take the 2 plus the 5 and divide by 2. That's going to get us 3.5. It's going to get us right in the middle. And that would be our x value of our vertex. Then what we would want is the y value. So you could plug in 3.5 minus 2 and 3.5 minus 5. What we would get is 1.5 times negative 1.5, and that's going to get us negative, what is that going to get us? 2.25. Okay, so here we're going to get negative 2.25. So if you were to graph this, this is what you would get. Okay, and you can see, yep, we're right there with our vertex, and there are our x-intercepts. Okay, just like we suspected, and then you could draw your U-shape. What if you have something like this? Alright, if you set this thing equal to 0, what we're going to have is x minus 1 equals 0, x minus 1 minus 1 equals 0. So our roots, or our solutions, would be at x equals 1 and x equals 1. This is weird to us, okay? So here would be what we call a duplicate root, or what your book tends to call a duplicate root, or solution. We call these bouncers. Alright, what we could do is we could rewrite this as x minus 1 squared, right? This is a square. So bouncers or double roots, what they do is they bounce off our graph. So this x minus 1, it tries to make it into the x-axis club, but what happens is it's going to bounce right off that x-axis. It will make it to that door, but it won't get through. So this is actually what the y equals x minus 1 squared looks like. There is our double root. There's where it would bounce. Sketch the graph of this. There it is. It's going to bounce right at that double root of x equals 3. Right? Sad face because it's negative. We could also use vertex form, so let me go ahead and use vertex form here. You can also identify where your vertex is. It's at 4, negative 2. We use the factor form to go from a graph to an equation. Now what we're going to do is we're going to go use this graph and get it into the vertex form. X minus h squared plus k is what we'll use. So we have y equals a times, and this is where we can go ahead and just plug in our h, or in other words, the x value of our vertex. So 4 squared plus, and then negative 2. So in this case, I'm going to say minus 2. Alright, and if you looked at this, what you would say is my standard form, my parent function x squared, would have been shifted to the right 4 and down 2, and you can see that that is the case. Now here's the thing, we still have to solve for that a. So again, I'm going to use that y-intercept, and what we're going to have is 14 equals a times 0 minus 4 squared minus 2. Be careful with the order of operations for this one. So we're going to have negative 4 squared minus 2. I'm going to keep simplifying where I can. Alright, so here I'm going to do exponents first because exponents would come first. A times, and then what is that, 16 minus 2. Alright, we would never try to subtract before we multiplied. We could do exponents before we multiplied, but we cannot subtract before we multiply. So we're not going to want to simplify this. This is where we're going to start undoing. So I'm going to add 2, 16 equals a times 16. Again, I probably should have varied this up again, but our a is 1. So go back to your original, here, and plug in that 1 for an overall result of y equals, and then x minus 4 squared minus 2. Done. Okay, so that's another way that you could also look at a graph and come up with the equation by using the vertex. You probably wouldn't have wanted to use factored form because these x-intercepts are a little shady. We're not exactly sure where they are. So when going from a graph to an equation, use either the vertex form or the factored form based on what information you know you can find. Do not forget to solve for your a. Alright, make sure you solve for that a. You pick a point and fill it in for the x and y. You cannot pick an x-intercept. Alright, so when you're solving for a, do not pick the x-intercept to plug in for your x and y to solve for a. And then FOIL carefully and use PEMDAS to get back into standard form. So here are your practice problems. Alright, and then I am going to do one more example directly from your homework. I actually can't remember what number this is, but what they do give us, I think it's 65 actually. What they do give us instead of a whole graph is they give us some key points. So they gave us a vertex and they give us a point. So I went ahead and plotted those on GeoGebra, and there's where we get them. So negative 2, 5 is there, and 0, 9. So if you wanted to, you could kind of sketch in a parabola if you wanted to, but you don't even have to do that. What we can go is go immediately into that vertex form because we know our vertex. So I'm just going to plug these values in. We have x minus negative 2, so x plus 2 squared plus, and then here's the y value. The k stands for the y value of the vertex, so here we have 5. But then we have to solve for a. So this is where I'm going to take that point that they gave us, that 0, 9. 9 is my y value. And then 0 plus 2 squared plus 5. So here I have 9 equals a times 4, because I'm going to take 2 squared plus 5. Shoot, sorry, I keep picking bad a's. But here we have 4 equals a times 4, and then when we divide, sadly, we get a equals 1 again. So this is just 1 for an overall result of y equals x plus 2 squared plus 5. If you wanted it in standard form, which the directions don't indicate, but you could do that by just foiling this out, we would get y equals x plus 2 times x plus 2 plus 5, and this is where you just have to be careful of the order of operations. We're going to get x squared and then plus 4x plus 4 when we FOIL that all out, and then plus 5, so y equals x squared plus 4x plus 9. There's our standard form. One last thing, this is a quick intro into what we're going to be doing in the next couple of days, but here's one application of a quadratic. It's a projectile motion function that's an object that's been thrown straight up into the air. So we will use just our standard form quadratics where we have ax squared plus bx plus c equals h, and what this does is it gives us the height of a thrown object with respect to time. So input in a certain time, we're going to get a certain height. And there are three factors that affect a height of an object that's thrown. Think about when we did those cannon projections with the vectors. I mean, it depended on gravity. All right, what we use is half of gravity for our A, so you can see that right here. It's either going to be negative 4.9 if it's in meters, or it's negative 16 if we're in feet. So that's what our A would be. Another thing that the height of an object that's thrown depends upon is how hard you threw it. That's going to be our B, all right, so the initial velocity at which the object was thrown. And then this C is going to be that initial height, because of course if you're on a cliff, the height of that object is going to be different than if you were just standing on the ground level. So we'll need all of those. Hopefully that's kind of familiar with just that horizontal displacement of an object that's a projectile motion object. So let's look at Grant for a second. And you don't have to write this down, I just want you to consider this situation. Grant throws a ball up from his waist level at 1 meter above the ground. He throws it at a speed of 18 meters per second and means to catch it, but it misses and falls to the ground. What I want you to do is consider, when will the ball hit the ground? Could you find that out? What is the maximum height that Grant's ball reaches? Can you figure that out? And when does the ball pass the point at which it was released? So I just want to give you a visual of what's going on here. If you were to graph this is going to be time in seconds and then the height in meters. So he's standing waist level, and then the ball is 1 meter up in the air at time 0. What he's going to do is he's going to release that ball. Okay, so after 0.9 seconds, it's going to be at a height of 13.2. At 1.8 seconds, it's going to achieve a level of 17.5 meters. All right, so if you wanted to know what was the height after 1.8 seconds, it's going to be 17.5. Calm down, Grant. I know you have the tendency to just be all crazy in class and just crazy and freaking out, but you got to calm down here. Okay, so he misses it, and that's where it lands. So I want you to notice that this is our graph that just occurred to display what happened here with this relationship of time and height of a projected object. So just consider that. You don't have to do it, but I'd like you to consider it. All right, good luck.